Good morning, guys. Quick introduction to today's lesson. And so hopefully we don't have too many of these remote learning lessons, but we've got one today and it's a double period, so want to keep you up to date. So today's lesson is about ionic bonding, chapter 4. And by the end of it, want to be able to draw electron shell diagrams to explain ionic compounds, and to be able to explain the properties of ionic compounds using the ionic bonding model. And so some activities that we'll be doing, or for you to do. Number one, there's this link to click view. There's a worksheet from the student workbook, the ionic bonding model, which is about explaining the properties. And there's a series of questions on page 89, question 1 to 12. I've put also up a PowerPoint in resources. So in here, that there's, in the chapter 1, there's this one called chapter 4, ionic compounds. And that's where I'm about to go to now. So in this one, this one begins. So the first part of this chapter links back to what we were learning about atomic structure and to explain how that forms ions. And so pretty simply, atoms can gain or lose electrons and become more stable, what they refer to as a noble gas electron configuration, like helium, neon, argon, those ones on the right hand side of the periodic table. Key differences: the metals lose electrons. It's why they're metals. They're going to have 1, 2 or 3 electrons in their valence shell, and they will lose them. They will become positive, so we call them cations. We write that charge as a superscript, and so lithium, 1 valence electron will become Li positive. Magnesium, 2 valence electrons will become Mg2+. Aluminium, 3 valence electrons will lose all of those 3 valence electrons and become Al3+. And you write the number and then the charge. And just remembering that the metal cations were also a feature in that metallic bonding, where the valence shell was delocalized. Here we've still got the metal cations. So the metals lose electrons, the non-metals gain electrons to get 8 valence electrons, and they become anions. So there's some sample problems on this one here. Notice if you're using the electronic version of the text, that there's a video you can watch explaining how to do this one sort of problem. But it's asking you to write the symbol, charge, and name of the ions you'd expect atoms of the following elements to form. So Mg, we have to find it. It's magnesium. It's got 12 electrons. And so that electron configuration is going to be 282. Yep. And so in order to become stable, the magnesium electrons loses those 2 valence electrons, and so it becomes Mg2 positive, the magnesium ion. S is sulfur, which is element number 16. So its electrons, the first shell 2, second shell 8, and then it's got 6 electrons in its third shell. And so to become stable, it needs 2 electrons to complete its outer shell. The charge is then going to be 2 negative, and we call that a sulfide ion. The couple of ones for you to try: Ga and P. So the next thing to look at is what we call ionic bonding. And so the cations and anions attract each other by electrostatic attraction, that attraction between positives and negatives. And so because they're both ions, this is called an ionic bond. And because we've got two different elements involved, we've got a compound, an ionic compound. One of the things that we use to explain ionic bonding is our electron shell diagrams. You'll remember these from when we were learning about electron configurations. And this is a nice way of visualizing what's happening. So if we're looking at the bonding between sodium and chlorine, we can remember sodium element number 11, 3 shells, 2, 8, 1, and it's combining with chlorine, element number 17, 2 in that first shell, 8 in that second, and then 7 in that valence shell. So sodium's the metal, going to lose its electron, its valence electron, and become, now it's just got 2 shells, 2, 8, and it's the sodium ion. And that electron went to chlorine, and so now we've got 8 in the third shell of chloride. And interestingly now, the chloride ion is now bigger than the sodium ion because this has gone down to 2 shells. If you remember, one of the trends in the periodic table was that sodium was actually bigger than chlorine. Now that they're ions, this is smaller. Next section is trying to link the structure of an ionic compound to its properties. What are the properties? Ionic compounds are normally hard, which means they're difficult to scratch. They're brittle, which means that they're shattered when they're hit. And that they're crystalline, which means that when they're pure, that they can be transparent or translucent, basically like the jewels, the gems. They've got generally high melting and boiling temperatures, and they don't conduct electricity as solids, but they do conduct electricity as liquids. And we can explain these properties with the ionic bonding lattice, shown here. Just like in metallic bonding, a lattice is that continuous 3D stacking arrangement. Unlike the metallic bonding lattice, in this case the negatives are the non-metal anions and they can't move through the lattice, unlike in, if you remember metallic bonding last week, that was the delocalized electrons which could move. And so we can use this to explain a whole series of those properties. Pretty much all of them come down to that fact that the attraction between the ions, the electrostatic attraction, is strong, and it's in a lattice, so it's continuous throughout that lattice in all directions. For example, it's hard. To scratch it means you need to separate some of these negatives and positives, and that's difficult, that's hard. Brittle, I think I showed this diagram last week. If you can apply enough force, you can shift one of these lines of the lattice so that now the negatives are lined up with the negatives, the positives lined up with the positives, and they repel each other. And so if you can apply enough force for that to happen, that you get this strong repulsion force and they'll shatter. The next, the crystalline, because in this one the electrons are, are bound to the ions, they're localized in the ions, that there are gaps where the light can pass through. Unlike in the metallic bonding, where the electrons were delocalized and they could reflect the light back to us, giving that shininess. Number 4, the high melting boiling temperature. It's a strong attraction between a negative and a positive, so it takes a lot of energy to disrupt it. they don't conduct electricity as a solid because they've got charges. Remembering that for electricity we need charges that can move. We've got the charges, we've got the cations and the anions, but they're all packed in together, and so they can't move. When they're liquid though, that these can move around each other, and you've got the charges and now the freedom to move, and you can get electricity.